Picture this: AI not just searching for keywords but truly grasping the intent behind your query. An AI that doesn't just retrieve what you ask for but what you actually need to know. Welcome back to the third video in our Advanced RAG series, where we are following the journey of Techno Health Solution and how they implement RAG for their several use cases. Today, we are unlocking one of the most efficient indexing techniques, multi-representation indexing. In this video, we'll talk about what is multi-representation indexing, why is it used, when it is used, where it is used, and who benefits from it. And finally, how it is implemented in LangChain. Let's begin. What is multi-representation indexing? Based on the paper Dense X Retrieval or Proposition-Based Retrieval, multi-representation indexing involves creating and storing representations of each document within the retrieval system. Representations here could mean traditional keyword analysis, deep semantic understanding or summary, and even visual elements like images or diagrams of the document. Why is multi-representation indexing used? Multi-representation indexing improves accuracy, adapts to different types of documents, and is flexible enough to handle complex information. The primary motivation for employing multi-representation indexing includes improved retrieval accuracy. By capturing different aspects of document content, this method leads to more relevant results for diverse queries. Contextual understanding. It enhances the system's comprehension of the context in which terms are used, allowing for better handling of nuanced queries. Flexibility for document types. It adapts to different document formats, accommodating varying user needs. Handling complex information, particularly useful for documents with intricate data such as scientific paper or code. When is multi-representation indexing used? Multi-representation indexing is particularly beneficial in scenarios where complex queries are common. Users often ask nuanced questions requiring understanding beyond simple keyword matching. Diverse document formats are involved. Environments where documents come in various formats and types such as academic, research, or product catalogs. Application require enhanced semantic understanding. For applications benefiting from deeper semantic insights such as conversational agents or advanced search engines. Where is multi-representation indexing used? This advanced indexing technique is applied across various domains, improving the relevance and depth of information retrieval. Search engines and information retrieval systems. Enhancing search results by utilizing multiple forms of document representation from text to visuals, ensuring more contextually accurate results. Conversational AI and chatbots. Boosting response accuracy by integrating multiple representations of both user queries and stored information, leading to more human-like and insightful answers. Who benefits from multi-representation indexing? End users interacting with AI systems such as search engines, chatbots, or recommendation engines benefit from more accurate and contextually relevant information. Some of them could be researchers, consumers of e-commerce platforms, knowledge workers who interact with AI tools, and developers and product managers who design AI-powered products can also benefit from improved retrieval accuracy. Now, let's understand how multi-representation indexing works with LangChain. Any other indexing pipeline in a RAG application, here obviously we have an indexing pipeline, but you'll see a difference here. Here we're introducing an LLM right in the indexing pipeline to summarize the process documents. Alright, so I'm going to quickly talk about this in sequence, and then we'll see how this entire application or the RAG application or the RAG solution works together. Like any other indexing pipeline, we have raw data. The idea here is that we are collecting or ingesting data from multiple sources, and these sources could be the internet or a data store like SQL or multiple shared locations or FTP, could be anything, right? And then we process those documents, and to process those documents you either can use these libraries like LangChain's document parsers, or we can use unstructured, which is essentially a very, very good ETL tool to process those documents. For this particular use case that I'm going to talk about, we'll be using a PDF. Think about in the use case of healthcare solutions, a lot of the documents could be in PDFs, or in fact in a lot of enterprise-based solution also, a lot of the documents could possibly be PDFs. And from a multiple representation or multi-representation context point of view, a PDF is a very good use case, because a PDF could actually have 3 representations, right? A PDF could have a lot of text, a PDF could have a lot of tabular data, tables essentially, and a PDF could also have images, and images with text embedded on it. So for us to essentially show this particular example, I think a PDF is a good example, right? So we need a solid parser that essentially can extract these 3 elements or these 3 representations from a document, and our document is a PDF here. Unlike a regular or a naive RAG, what we'll do here is, instead of passing the chunks or passing chunks to an embedding model and converting your vector representations, we'll first convert the chunks into the summaries, or basically create summaries out of the chunks. How do we do that? We obviously use a large language model to do that. What we would do next is, we would basically take the summaries and convert them into their vector representations using an embedding model, and store the vector representations of the summaries into the vector data store. All right. While we are doing that, we will also take the chunks as a whole, or the documents as a whole that we've just parsed using unstructured, and store that in a doc store. And this doc store could be a key value doc store or a NoSQL doc store, depending on the use cases that you have. All right. Now, what would happen once a user would essentially query is, the query would first go to a multi-vector retriever. Multi-vector retriever is a LangChain package or a LangChain module, where it can essentially do a similarity search on top of the vector database, meaning that this particular query is converted into an vector representation using the same embedding model that we have used in the indexing pipeline, and that vector representation of the query is sent to a vector database for a similarity search. Now remember, this particular vector data store has the summaries of the documents as vector embeddings. So essentially the query is, we run a similarity search on top of the summaries, we get the relevant summary, and we also get the relevant doc store of that particular summary. And what is passed to an LLM as a prompt, essentially, there is a step here where we craft a prompt, and that prompt would essentially entail the query, the original query that came from the user, and the entire document, not the summary, but the entire document that we essentially got as a mapping of the summary and the doc that we did here in the indexing pipeline stage, and that is essentially passed to the LLM. The LLM then, depending on the instruction that is given to it, generates a response, and that response is essentially sent back to the user. It's a very simple implementation, but it's going to be a very efficient one. Much better than a naive implementation or a naive RAG implementation, right? Let's look at the doc type that we will be parsing. Since we are building this solution for Techno Health Solutions, or Techno Health Solutions essentially is building the solution for medical representatives or medical professionals, we'll be using an example of a lung cancer document. This is a 2024 document. This is available for free on the internet. I will also be sharing this with the source code. Now, this is a good use case because this has a lot of raw text, as you can imagine, in a PDF, and also it has a lot of tabular data, right? Now, let's assume that we were passing this, we would use a regular PDF extractor or a PDF parser and extract text from this, and then pass or store that into vector store, by converting them into their vector representations. That would not be very efficient, and or at least the quality of chunking and the quality of text that would be stored in a vector store would not be very, would not be of high quality. This is where using an ELT tool like unstructured comes into picture, because what it will do is it will perform post-processing to aggregate text that falls under each title here, and perform further chunking into text blocks for downstream processing based on the user specific flags. I will show the flags in a bit. I will show the code to you guys in a bit. All right. As you can see, there is a lot of table data here, and there are a lot of raw text as well, and we'll need both of this. So we have two representations coming from this particular PDF. One is raw text, a lot of text, as you can see, and its tables. All right. So we will use unstructured to essentially convert this particular PDF into 2 representations now. All right, let's actually go to the code and see how we would implement this. All right, so what you're seeing on the screen is essentially a notebook that you will find in the cookbook directory of the LangChain repository. You can download that. I'll also share this as part of the description here. Something that you'll have to do first is you'll have to download the NLTK 3.9.1 package. At least that's what that was working for me. The 3.8.1 which I had previously installed was not working correctly. So this is something that you want to take care of. These are all the packages that you have to install. The other packages that you'll also have to install is the Tesseract library and the Tesseract package, and the Poplar package to essentially process PDFs, right? I have this already installed. We'll essentially move to the part where we'll load the document. You want to check if we are using unstructured partition here or unstructured partition.pdf here to convert 2 representations from the PDF. One is the table data or the table elements, and to extract the text elements from this. These are the settings that you'd want to give. Because we are not using an image, I'll set this to false, and essentially I'm also passing the chunk size that we want. The chunk size could also vary depending on the kind of embedding model that you're using, and also the context window of your LLM that you'll use essentially to parse, or because you'll be passing that entire chunk as input, so you'd want to take that into consideration and set these parameters accordingly, right? Now, I'm sorry, depending on the kind of PDF or the size of the PDFs, this could take anywhere between 5 to 20 minutes. In this case, it has taken 5 minutes for this particular PDF to be parsed. All right. Then the first thing that we do is we check the kind of we will basically create a dictionary to store counts of each type. Remember, we are trying to have 2 representations here. One is a text representation as well as the table representation. We will see the count of both, and as you can see here, we have 24 text representation or 24 text elements that have been captured and 5 table elements that have been captured. But remember, it has essentially using its post-processing methods to sort of condense a lot of information into one particular element, and we'll see that in a bit. All right. Then what we'll do is we create an element class to essentially capture the type, which is in this case a table or raw text. We'll first create a chain to essentially summarize the chunks that we've just extracted from the PDF, and we have 2 chunks essentially, or 2 elements. One is table element and the text element, right? We will create a summary chain first, and I'm using OpenAI's GPT-4o mini model here. And what we'll do is we will first summarize the particular table elements, and once this is run, this is how the table elements look like. As you can see, it was able to essentially summarize pretty much each row of the table here, and also not just summarize but also expand on certain abbreviations that it found out. For example, if you look at this, let me scroll up, I think it is the top one. Yeah, so if you look at this particular row, checkmate 017 NCT something, so it was able to take that as a title, that is study, and it was able to summarize the findings here, combining both key findings as well as the primary endpoint. And it has also expanded on abbreviations here. For example, advanced SCC here means advanced squamous cell carcinoma. We'll do 2 things now. We'll essentially have to build the pipeline, the ingestion pipeline. How do we do that? We first, after we have extracted the unstructured or the raw elements and then summarize them, we will have to store those summaries into a vector store. We'll use the ChromaDB here, and I'm using OpenAI's text embedding 3 small model, and to store the chunks as a whole, not the summaries but the chunks as a whole, we'll be using the in-memory store. So remember, we are storing the summaries in the vector store, and we are storing the documents as a whole in an in-memory store. Let me go back to this particular design so that you understand that. We are storing the representations in the vector database, basically the summary, the vector representations of the summary into a vector store, and we are storing the documents as a whole in a doc store. All right. Let's quickly run this particular query now on top of our vector store to see what kind of document it returns. And we'll obviously look at the most similar document this is returning. So the query is, what is dual immunotherapy without chemotherapy? And the document returns the document that is written. This is, remember, this is a summary, right? This is not the actual document. The summary looks something like this. And this seems pretty neat. We will then see what is the kind of document that it returned as a whole. And if you see you'll have to use the retriever object that you just created of the multi-retriever module or the multi-retriever class. We will pass the query and use the invoke method of the retriever object, and this is the first document that is written. All right, now let's create a RAG pipeline to see how all of this works together. Now before I run this particular snippet, I'd want to show you what is happening. Let me go back to that particular design. So the user essentially queries. The query is converted into a vector representation using the same embedding model that was used in the indexing pipeline. It is passed, the query is essentially passed to a multi-vector retriever object as question. Multi-vector retriever runs a similarity search against the vector database. Remember, the vector database has the summaries of the documents or the representations of the document that we have, we created using unstructured library. And then depending on the document, the similar document that was written, the related original doc stored in the doc store is essentially returned or sent to the LLM. Now, how is this done? Is basically the multi-vector retriever, as we saw here in the retriever.invoke method. Let me go back here. The retriever.invoke method returns this particular document, the raw document. That particular raw document is essentially sent to an LLM with whatever instructions. In our case, our instruction is simple: answer the question based only on the following context, which can include text and tables context, right? So the raw information is sent, the raw document is sent, or the chunks of the document is essentially sent to the LLM. The LLM uses that particular information and is generating this clean response. Now let me actually use the same query that I used here. What is dual immunotherapy and chemotherapy? I'm going to run the same here. I should get a response soon. Alright, this is the response we're getting. Dual immunotherapy without chemotherapy refers to a treatment approach of metastatic non-small cell lung cancer that involves the use of 2 immunocheckpoint inhibitors. Now, what we need to understand here is that it is not just the kind of document that was passed to the LLM, by the multi-vector retriever, but it is also the kind of document that it picked up, and what helped it pick up the most relevant document. Not just the most similar, but also the most relevant document is the semantic representation of the embeddings, meaning that a lot of the chunks were essentially converted to a summary. It used the summary to generate the, to essentially come up with the most relevant document. But the mapping that was done in the indexing pipeline, where the summary as well as the relevant chunk that were stored in the doc store, that was picked up and sent to the LLM essentially. Alright guys, I hope this was helpful. This was multi-vector representation. This is video 3 of the advanced RAG series. If you have not seen video 1 and video 2, I very strongly recommend that you do, because we are using a use case of a techno health solution which is intending or trying to build a rack solution for healthcare professionals. We'll use this as the premise for all our videos going forward. Thank you so much for watching. You have a good day. Bye.